Algebra 2, Chapter 6, Section 2, Fractional Exponents and Radical Expressions. First of all, I just want to say a radical in this context does not mean crazy or extreme. It means square root, basically. And we'll see what radical means as we use it. So a radical expression is an expression involving roots. That may not help any. A root. What is a root? Well, let's think about this for a second. The square root of a is the positive number who, when we square it, is a. So the square root of 4 would be what number do I multiply by to get 4 when I multiply it by itself? Well, it's 2 times 2. So the square root of 4 must be 2. Okay, so 3, since 3 squared is 9, the square root of 9 is 3. And we could write a 2 here to help us remember this is a square root. Okay? That's just assumed that this is square root when there's no number. But we can extend this idea to any base where we're trying to find that base to an nth root power. Okay, so really I think this should say roots can be extended to any exponent. Okay, so the nth root of a is the positive number b such that, and this is, I'm sorry, this is a mistake. When we're talking about nth roots, it's a number. It doesn't have to be positive. It could be negative, actually. The nth root of a is the number b such that a is equal to b to the n. Okay, so that may be really complicated, but we'll do some examples to make it make sense. So, in other words, if I can write the nth root of a equals b, implies that a, this number a, is equal to this number b to the nth power. Okay, so the fourth root of 16 is 2 because 16 is equal to 2 to the fourth power. So we're trying to find what number when I take this power 4 to that number gives me 16. Okay, or we could have the fifth root of 32 equals 2 as well, because 2 to the fifth is 32. Okay, we're trying to find what number, when I multiply by itself 5 times, in this case, is 32. The cubed root of 9 is 3. No. Cubed root is the square root. The cubed root of 27 is 3, because 3 cubed is 27. Now, what about negatives? So, if I say what's the cubed root of negative 27, that's why I scratched this positive out here. It's positive when we're talking about square roots. A cubed root, if I say what's the cubed root of negative 27, the answer is negative 3, because negative 3 times negative 3 times negative 3 is negative 27, because there's an odd number of negatives. With the square root, we say positive, or really any even power. We're interested in the positive number because the negative number also gives the answer. Right, so in other words, there's 2 square roots of 4, actually. Square root of 4 could also be negative 2. But here we define the square root to be positive so that we only have the positive root as being interesting. Right, negative 2 times negative 2 is 4. Just like 2 times 2 is 4. Because the negatives cancel. Because of that, too, if we say what is the square root of negative 4, we're asking what 2 numbers can we multiply to make negative 4? Well, there are no such real numbers. No such real numbers. So right now we'll write no answer. Later on we're going to learn about some other numbers that aren't real numbers that actually give us a way of expressing the answer. Okay, so but right now we can just write no answer. And we can abbreviate real numbers with this funny R, which is called a blackboard R. That means the set of all real numbers. So there's no real numbered answer. So with all that said, let's try practicing. Let's evaluate these. The square root of 121 What number do I multiply by itself to get 121? 11. 11 squared is 121. The fifth root of negative 32 would be negative 2. Because it's an odd one, I can do a negative. And negative 2 times itself 5 times is negative 32. Square root of negative 4 is, there's no real, can't write right now, there's no real valued solution. You can also just write no answer. It's fine for this part of the class. What's the fourth root of 81 over 625? Well, 81 is the same as 3 to the fourth power, because 27 cubed, sorry, 27 times 27, I can't talk. So think about this. 3 times 3 times 3 times 3, that's 9 times 9, which is 81. Okay, so the fourth root, this is 3 to the fourth. The fourth root of 81 is 3. And applying this idea of taking the fourth root of the numerator, the fourth root of the denominator, the fourth root of the denominator, and we'll explain why this is true in a minute, would be the fourth root of 625, and 5 times 5 times 5 times 5 is 5 to the fourth power. 5 times 5 is 25. 25 times 25 is 625. So this is 5. The fourth root of 625 is 5. So the fourth root of 81 over 625 is 3/5. So let's talk about how radicals are related to fractional exponents, part of our title here. Since the number 4 we can write as 4 to the first power, and that would be the same as writing 4 to the 1/2, just a half, times 2, because a half times 2 is just 1. And then we could split this up using the common, the exponent to an exponent rules that we learned, where if we have a multiplied exponent, we can rewrite this with parentheses and do this first and then take the final exponent. So this inner part here is 4 to the half power, which we've not defined yet. We will in a second. And the outer part is squared. So we're multiplying this number by itself and getting 4. Okay? Well, that means that number that we're multiplying by itself must be 2. And also it must be the square root of 4, because if we multiply the number by itself and get it, that's what it means to be a square root. Okay, and this idea leads us to expressing radicals as fractional exponents. So we can rewrite, these are equivalent things, the nth root of a as a to the fractional power 1 over n. So if it's square root, it's the same as the 1/2 power. If it's cubed root, it's the same as the 1/3 power. If it's the fifth root, it's the same as the 1/5 power. So with that knowledge, let's evaluate some expressions. 25 to the 1/2 power is the same as the square root of 25, which is 5. 9 to the minus 1/2 power, well, what does that mean? Well, we can apply our rules of exponents to change the negative power to a positive power. This would be 1 over 9 to the 1/2 power, which is the square root of 9, which is 3. So it would be 1/3. 8 to the 1/3 power would be the cubed root of 8, which is 2. 2 cubed is 8. This would be 1 over 27 to the 1/3, which is the cubed root of 27, which is just 3. 64 to the 2/3 power. What do we do with this? It's a little confusing at first, but if we think about it, we can split this up into two numbers. We can split this up into 1/3 times 2, which means we can use the rules of exponents to write 64 to the 1/3 power squared. Okay, 64 to the 1/3 power is it 8? 8 times 8. No, not 8. Let's try 4. 4 times 4 times 4 would be 16 times 4, 64. So 4 is the cubed root of 64. So that would give us 4 squared, which is 16. So 64 to the 2/3 power is 16. 9 to the negative 3 halves would be 1 over 9 to the 3 halves, which would be 1 over 9 to the 1 half cubed by the rules of exponents and splitting up like we did here, which would be 1 over 9 to the 1 half is the square root of 9, which is 3. 3 cubed. 3 cubed is 27. So 9 to the negative 3 halves is 1/27. Here we have negative 216 to the 1/3 squared by breaking this up into two numbers and applying the rule of exponents, where we're exponentiating an exponentiation. Well, 216 to the 1/3 power, we need to find what number do we multiply by itself 3 times and get 216. And with a little thought or trial and error on our calculators, we would get the answer, which is, hold on, let me find it, that way I don't have to do my trial and error myself. Let's see, the cubed root of negative 216 would be negative 6, because 6 times 6 is 36, and 36 times 6 is 216. So we would have negative 6, negative is an odd power, we can preserve the negative. Negative 6 squared would be 36, positive. And last but not least, h, we would have minus 625 to the 1/4 all cubed. Here we have an even power, 1/4. So this would be the 4th root of negative 625. Since it's an even power, we can't use a real number to get to a negative answer. We can't multiply a number by itself an even number of times and get a negative. So the answer is no real numbered solution. Let's write each form in the form of x to the power, and then give the value of the power. So we're going to have to use fractional exponents potentially here for our radicals. So remembering the rule that we can negate the power, this is just x to the minus 3, n is minus 3. Here we would have fractional exponent, x to the 1/5, so n is 1/5. X's cubed root would be 1/3, so we have x to the 1/3 squared. Using the rules of exponents, that would be multiply the powers, we get 1/3 times 2 is 2/3, so n is 2/3. Square root of x to the 5th would be x to the 5th to the 1/2, multiply the powers, x to the 5 halves. So you notice here the order actually doesn't matter. We could write it this way or we could write it this way. This is the same thing. In other words, x squared to the cube root of x squared is the same as the cube root of x squared. The order there doesn't matter because we can multiply the powers in either order. Right, it's the same as if we had 3 squared all cubed. That's the same as 3 to the 2 times 3, which is the same as 3 to the 3 times 2, which is the same as 3 cubed squared. So here we have x to the 5 halves, n would be 5 halves. Using the negative rule, we would have x to the negative 1/4, so n would be negative 1/4. And here we would have on the inside negative 1/2 as our exponent times 3, so we have x to the negative 3 halves, n would be negative 3 halves. Simplify each expression and assume all the variables are positive. Okay, well we could use the common power rules here to combine. So we would have, this is 2 to the 1/3 power times 4 to the 1/3 power. Remember the common power rule was now we multiply the insides and take it to the 1/3. 2 to the times 4 is 8. 8 to the 1/3 is the same as the cube root of 8, which of course is just 2. Part B, we have z to the 6th times w to the 9th all to the 1/3. So we can use the rule we just used here in reverse to get z to the 6/3, which 6 divided by 3 is 2, and w to the 9/3, which is of course 9 divided by 3 is 3. We have z squared w cubed. Again, better cross your z's. Combine the radicals if possible. So this is some practice with addition. So just like 3x squared plus 4x squared equals 7x squared, we can add coefficients of the same radicals. So here we have the square root of 7. That's the same number. So we can add coefficients. 9 square root of 7. Here we have square root of x, same number. Add the coefficients. 4 plus 3, 7 minus 1 is 6. Now we have the cube root of 2, the cube root of 2, and the square root of 2. Well, we can't add the square root of 2 in because it's a different number, but we can add the coefficients to the cube root of 2 to get 14 times the cube root of 2 plus the square root of 2. Here we don't have the same radical, but we can transform square root of 20 into square root of 5. How can we do that, you might think? Well, we can think of this as a fractional power, and think of 20 as 5 times 4. Well, then we could split the 5 and 4 up using the rule of exponents, the same exponent. We would have 4 to the 1/2 times 5 to the 1/2, and 4 to the 1/2 is just 2, and 5 to the 1/2 is just the square root of 5. So 2 times 8 is 16, square root of 5. And once you get the hang of this, you don't need to convert and back and forth between two forms. You can actually just say square root of 20 is the square root of 5 times 4, which is the square root of 5 square root of 4. Okay? Without having to convert into exponent form. 16 minus 5 is 11. So you have 11 square root of 5 is the answer to part D. Part E, we have 5, and here we're going to need fractional exponents. 4x cubed to the 1/2 plus 3x, 36x to the 1/2. So let's combine things and see what happens. So we have 5, 4 to the 1/2. Remember, we have to take the 1/2 power of 4 and the 1/2 power of x cubed. So the 1/2 power of 4 is 2. Remember, square root of 4 is 2. 1/2 power of x cubed is multiply the exponents, x to the 3/2. Plus 3x, 1/2 power of 36 is 6, because 6 times 6 is 36, x to the 1/2. 5 times 2 is 10, 10x to the 3/2. Plus, and then distributing this, we have, that's not really distributing, just multiplying all this together. 3 times 6 is 18. X times x times x to the 1/2. We have the same base now. Same base. Add the exponents. Well, remember the 1 to the first power is just implied by any number. So we would add 1 and 1/2 to get 3/2. And now we do have the same thing here, x to the 3/2, x to the 3/2. We can add the coefficients to get 28 x to the 3/2. A fraction with a denominator containing radicals is hard to compare with other fractions. So if we have 2 over the square root of 2, for instance, that's kind of hard to compare with other numbers or other fractions. So we would want to make this rational by not having a irrational number or a radical number in the in the denominator. So we would want to rationalize this. So we could rationalize this by multiplying by, rationalize this expression. Let's put it down here. 2 over the square root of 2. we can rationalize this by multiplying by the square root of 2 over the square root of 2, and we would get 2 square root of 2 over square root of 2 times square root of 2. Well, the square root of 2 times the square root of 2 is 2, because you have 2 to the 1/2 squared. Okay. So if I do it too fast here, 2 to the 1/2, 2 to the 1/2. So that would be 2 to the 1/2 squared. 2 times 1/2 is just 2 to the first, which is 2. Okay. And here the 2's cancel. We're just left with the square root of 2. So writing 2 over the square root of 2 is a lot harder to compare with other numbers versus just writing the square root of 2. So we always want to rationalize our fractions. Okay. Now we call it irrational because we can't make a ratio in the denominator. It's not a ratio of any whole numbers or any numbers of any sort. It's an irrational number because the square root of 2 doesn't have a way of representing it as a ratio. So whenever simplifying, any irrational denominator should be rationalized. So whenever you see simplify and you see an irrational fraction, you must rationalize it. So what about if we have a case not just like this, but we have 2 over 2 plus the square root of 2? How do we rationalize this? We rationalize this by multiplying by the conjugate of the denominator. What is the conjugate? So you have two things added together, a and b. The conjugate is a minus b. And why do we want to multiply by the conjugate? Well, think about the generic thing. We multiply by the conjugate, we get a squared plus b times a minus b times a plus b squared. And these cancel, and you're just left with a squared plus b squared. And if you have square roots, then squaring will get rid of them, and there won't be any square roots left. So let's practice this. Simplify by rationalizing the denominator. So we need to multiply by a fraction, which is the conjugate. Okay, that's the magic you've got to remember. So now we multiply the numerator. Don't forget our FOIL, or our distributive law. We have 2 times 2 is 4, minus 2 square root of 2, because we have to distribute. And the denominator, we have 2 times 2 is 4. We'll have 2 square root of 2 plus, 2 square root of 2 minus, which is going to cancel. Not going to bother writing that, and we'll end up with negative square root of 2 times positive square root of 2, which will be negative 2, because the square root of 2 times the square root of 2 is just 2, which gives us 4 minus 2 square root of 2 over 2. And factoring a 2 out of the numerator, I have 2 minus 1 square root of 2, which we just write as square root of 2 over 2. 2's cancel. We're left with simply 2 minus the square root of 2. So here we want to multiply by the conjugate of the denominator, 2 minus the square root of x over 2 minus the square root of x. And that gives us, using our distributive law, 2 square root of x. And we have minus square root of x times square root of x, which will give us minus x over, why did we drop the square root? Because you are multiplying the square root times the square root, which gets rid of it. It's squaring the half, which makes it just a whole power. And then in the denominator, we'll have 2 times 2 is 4 minus x. Okay, now there's no more radical or square root in the denominator. Now we're done. We can't necessarily simplify beyond just getting rid of the radical. Here we have a radical, we have a square root of p and a square root of q, but we'll get rid of both of them by rationalizing the denominator. So let's multiply by the conjugate, square root of p minus the square root of q over the square root of p minus the square root of q. That'll give us 1 times that, so we'll just have square root of p minus square root of q in the numerator over, And we'll have p squared, square root of p squared, which is just p minus square root of q times square root of q, which is just q. And that's it. That's all the answer. That's the answer. We don't have any other way to simplify, but now we don't have, again, no radicals, no square roots in the denominator. Again, we got to multiply by the conjugate here, so that we have, this is our a, this is our b. We need to multiply by square root of x minus 1 plus 1 over the square root of x minus 1 plus 1. Okay, so distributing the numerator, we get x times the square root of x minus 1 for first. For our inner, we'll have minus the square root of x minus 1. For our outer, we have x times 1 plus x. And for our last, we have minus 1. And then the denominator will have square root of x minus 1 times the square root of x minus 1 will give us x minus 1. And then we'll subtract 1 times 1, because that's what will be left. Remember, the outer and the inner parts cancel in the FOIL, and multiplying by the conjugate, that's why we do it. And we're left with x square root of x minus 1 minus the square root of x minus 1 plus x minus 1. All of this stuff over x minus 2. And we can also, I think a perfectly fine answer would be to not bother distributing the numerator, so maybe a faster and easier answer to get is to just write the numerator in the factored form, and then just write that over the rationalized denominator, x minus 2. That's probably a better way of writing this.